In this segment, I want to start Chapter 14. Chapter 14 is all about oscillations. What's an oscillation? Well, an oscillation is just a fancy word for something wiggling back and forth in a repetitive manner. And so all kinds of things oscillate in nature. So this primate here is swinging along this branch, and as he swings over with one hand, he grabs onto it, and then he swings and grabs the branch with his other hand. And each swing could be thought of as part of pendulum motion, right? And so a pendulum is a great example of oscillatory motion. And so here's this pendulum swinging back and forth. This is a great example of an oscillation, but it helps us model animal motion and all kinds of other things that we can model by understanding this simple phenomenon right here. So in order to wrap our brains around some of this stuff, we need some terminology, right? And so we need a common language so we can talk about these ideas. So first of all, we need words to describe how quickly something is wiggling back and forth. So, for example, here's this pendulum. It's wiggling back and forth. The period is how much time is required for one complete cycle. So one complete cycle would be over and back, 1, 2, like that. And this is pretty close to about a 1 second period, but let's just see for sure, right? Let's count 10 of them, and I'm going to get my stopwatch out here. And let's count 10 oscillations. Ready? Here we go. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I got 13.4 seconds for 10 oscillations. So what is the period of this motion? The period of this motion is 13.4 seconds divided by 10. Why divided by 10? Because the period is the time for one cycle, and I counted the time for 10 cycles. And so what is the period of that motion? 1.34 seconds. That is the period for that motion. It tells us how long it takes for one complete cycle. Now the frequency also just kind of tells us how fast the thing is wiggling back and forth. But instead of telling us the time for one cycle, it says how many cycles per second are happening. And the frequency is equal to 1 over the period. So if we wanted to write down the frequency for this pendulum, we would simply write this. And I'll have to get out my calculator. Let's see what that is. So I ran my calculator and I got 0.75. What are those units? Well, the units are 1 over seconds, and we can see why that is here, right? I'm just taking 1 divided by seconds. So my unit here is inverse seconds, or 1 over seconds. We have a fancy name for it. It's hertz, and we represent that right here. And so what does that tell us? That means that there are 0.75 oscillations per second, or it completes 3/4 of a complete cycle every second. Recall that a complete cycle is from the beginning all the way to the end. So this is a quarter cycle, half a cycle, 3/4 of a cycle, 1 full cycle. In other words, it takes 1 second for this to go from there back to there. So 3/4 of a cycle per second, that's its frequency. We could have done the same thing with this. This is my mass on the spring, right? So there's all kinds of oscillations in nature, but the two systems we're going to focus on in this chapter are the pendulum, as illustrated here, and the mass on the spring. And so here I have a spring, and there's a mass here, and it oscillates like that. Up and down, up and down, up and down. Okay, those are the two systems we're going to focus on. We need to remember a term from a number of chapters ago, and that term is equilibrium. What does equilibrium mean? Hopefully you said to yourself, equilibrium means that the net force on an object is 0, which implies that the object is not accelerating. So an object that is in equilibrium has no net force on it, and that means that it's not accelerating. The equilibrium position for an oscillation is the point at which the net force on the object is 0. And we can see that if we just let these two systems come to rest, then they will come to rest at their equilibrium position. And we can tell that this is their equilibrium position because the net force on them is 0. I can tell that because they're not accelerating. So I've made some marks here where the equilibrium positions are for my two systems. For the mass on my spring, my equilibrium position is right here. For my pendulum, it's right here. And again, why do we say that? Well, they're not accelerating at that position. Now, if I was to displace this from equilibrium and let it oscillate, it turns out that as it passes through that same position, well, whether it's moving or not, the net force on the object is 0. So that is the equilibrium position, whether the object is moving or not. So the equilibrium position is right there in the middle. Now, in order to have this oscillating motion, this repetitive motion, we need to have something that's called a restoring force. And the restoring force is just some force that always points back towards that equilibrium position. Let's take the pendulum, for example. If I displace the pendulum in this direction, the net force on the pendulum is in that direction, towards the equilibrium position. I can tell because if I let go, it accelerates toward the equilibrium position. If I displace it over here, though, now the net force is in that direction. Again, toward the equilibrium position. So the restoring force is always a force that points back to the equilibrium position. And in order to have this type of oscillating, repetitive motion that we're learning about in this chapter, we need to have a restoring force. How about the spring and the mass? Does it have a restoring force? Absolutely. If I lift the spring up, the mass up a little bit, and I let it go, then it oscillates. And what direction is the net force in? Towards the equilibrium position. So if I lift it up here, it will accelerate down towards the equilibrium position. Indeed it does. However, if I pull it down here and let go, then it will again accelerate toward the equilibrium position. It is a restoring force because it always points back toward the equilibrium position. So that middle point is the equilibrium position. The points of the greatest swing are called turning points for obvious reasons. That is where the mass turns around. So right here, a turning point. Right here, a turning point. Right here, equilibrium position. Equilibrium position, turning point, another turning point. There are two turning points for any system. There is only one equilibrium position. A ball in a bowl is a lovely example of oscillating motion with a nice restoring force, right? The force always points, the net force always points back towards the center of the bowl. What carries it through that equilibrium position to keep it swinging? Well, it's its object's inertia, right? So there is no acceleration on the object as it passes through the equilibrium position, but it's already moving. It's got some kinetic energy, so it just keeps moving. As it goes over here, as it passes to this side, that restoring force slows it down until it turns around at the turning point, and then the restoring force speeds it up. Slows it down at the turning point, speeds it up. Okay. Again, this segment's all about terminology so that we have a common language and we can just talk about these concepts. Again, the restoring force is a force that always points towards the equilibrium position. The equilibrium position is the location where the net force on an oscillating object is 0. Intuitively, that's the center of the motion. Amplitude is another important term. Amplitude is the magnitude of an object's maximum displacement from equilibrium. So the amplitude then would be, how far did I pull this down before I let go? If we were to analyze this motion, we see that the ball, the mass, it goes from right here is where I start it. If I let it go there, then it's going to go up here to about right there, right? Something like that. There we go. Okay, for this motion here, the distance here is the amplitude. That is the amplitude. This right here is also the amplitude, right? So it should be symmetrical on either side here. The amplitude is the furthest distance from the equilibrium position that the object goes. So this chapter is all about oscillations. And oscillations are just one type of repetitive motion. There's all kinds of different types of repetitive motion. The Earth goes around the sun once a year. The Earth rotates on its axis once a day. My heart beats in a regular rhythm. All of these things are repetitive motion, and so they are periodic motion. We could describe them with either of those words. Periodic motion is just motion that has some well-defined period. And so here's an electrocardiogram of somebody's heart beating. And if you measure the voltage across somebody's chest, you'll get a pattern like this. And notice it repeats in time. That makes it periodic motion. But we're going to study a very specific type of periodic or repetitive motion in this class. We're going to study simple harmonic motion. Why? Why are we going to limit ourselves to that? Well, because in physics what we do is we start with the simple and we figure out a way to describe that. And then we say, well, we've got this nice model that works really well under these constrained conditions. Can we expand this model so that it describes things that aren't quite that exact, right? Or don't quite follow this exact pattern. And usually the answer is yes, right? And so this is what we do. We just start with the simplest situation we can, and then later, if we need to, we add complications in order to describe whatever realistic situation we have. So, again, we're going to constrain ourselves to something called simple harmonic motion. Now, what is simple harmonic motion? Well, simple harmonic motion is, in a word, this. Right? That is simple harmonic motion, and so is this. Well, what makes it simple harmonic motion? And why do we care about it? Well, what makes it simple harmonic motion is that the restoring force is linear. We'll revisit that in one moment. Why do we care about it? Because we can describe it with sines and cosines. Let's see how that works. It just naturally falls out, right? Sines and cosines just naturally fall out of simple harmonic motion. In order to help convince you of this, let's check out a video really quick. This is from MIT. So we got a paint can attached to some springs and a roll of paper. This is a very DIY kind of a setup. And so this gentleman's going to come, he's going to turn on the paint can and set it to oscillating, and then unroll the paper, and we'll just see what happens. And what kind of shape is that? That's definitely a sine or a cosine type of a shape, right? We would call that a sinusoid, right? Remember that the difference between a sine and a cosine is just where they start, right? The shape is identical. So we would call this a sinusoid. Is it a sine or a cosine? The answer is yes. Depends on where you call zero. Again, simple harmonic motion is well defined by sines and cosines. That shape just naturally fits simple harmonic motion. There's all kinds of wiggly functions in the world, but most of them you haven't learned about. Hopefully, you're pretty good at using sines and cosines. Okay, so we can describe this type of motion with sines and cosines. In order to get this kind of motion, we need to have a linear restoring force. Recall that the restoring force is this force that pushes back towards the center, back towards the equilibrium position, right? Anytime the object is above the equilibrium position, there's a net force pulling it down. Anytime it's below the equilibrium position, there's a net force pulling it up. Anytime it is to the left of the equilibrium position, there is a net force pulling it to the right, and anytime it is to the right of the equilibrium position, there's a net force pulling it to the left. That's what the restoring force is. Now, if that restoring force is linear, then we get simple harmonic motion. Now, the good news is that I'm not going to pester you with the details of this. Like, this is just what we're studying. If we're talking about wiggly stuff, we're talking about simple harmonic motion, okay? But it's important to understand how what we're learning is a bit constrained, but that's okay. In a more advanced course, we learn how to apply the same techniques to more complicated situations. So these are, again, the two systems that we're going to be really focusing on. Now, for the mass on the spring, recall that the force of a spring is always proportional to the displacement, right? Remember Hooke's law. Remember Hooke's law. F equals negative k times delta x. So what does this equation say? It says that there is a force on an object hooked to a spring, and that force is proportional to the displacement of the spring. In other words, the stretch of the spring, right? So there is a force. It's proportional to how far the spring is stretched or compressed, and it is in the opposite direction. Oh, that's a restoring force. Points back towards zero, no stretch or no compression, and proportional to the stretch of the spring. Okay, and this is true whether we have a vertical spring like this or if we have a horizontal spring as shown in the PowerPoint. It's much easier for me to model a vertical spring than a horizontal spring, since I don't have an air track in my basement and frictionless blocks and boards are really hard to come by. So I'm going to model my mass on a spring as with vertical motion. But the good news is it doesn't matter. It turns out to be the exact same math whether we have it hanging here or horizontal. It doesn't matter. Now how about this? Is the restoring force here really a linear restoring force? There's certainly a force that points back towards the center. Is it linear? Well, this one's a little trickier. In order to wrap our brains around this one, we need a new idea, and that is the small angle approximation. The small angle approximation says that when theta is very small, so when we're talking about very small angles, so here we're measuring, notice in the PowerPoint, we're measuring theta as the angle between the string and this vertical line. And so when theta is small, this is theta here. When theta is small, sine theta and theta are almost exactly the same. And we could see why that is if we were to do a quick sketch of the sine function. So there's the sine function. Right? And if we were to graph just, here, and so what have we got here? We've got theta over here. And up here we've got sine of theta. But if we were to graph instead theta versus, theta, that's sort of a funny thing to graph, but if you graph something versus itself, it's just a straight line, right? And so what does that look like? Well, it would just look like this. And so notice if we were to zoom in on this region right here, that the graph of theta and the graph of sine theta, they really overlap. And so this is the small angle approximation. When theta is small, sine theta is almost the same as theta. And what is the restoring force? Well, we could set up a coordinate system here where we have, a tangential axis and a radial axis. So maybe we'd call this the y direction, and maybe we'd call this here the x direction. And so we could break the we could break the weight down into components. In the x direction, or the tangential direction, we would have w sine theta. And in the radial direction, or what we might be calling the y direction here, we would have w cosine theta. Recall we did this quite a bit in chapter 5 for motion on a ramp. So if this component here is w sine theta, as long as the angle is very small, then we could write this as w times theta. The restoring force then is equal to w times theta. And we'll go ahead and put an approximately equal sign on that one. So we have a restoring force that is linear. It's proportional to the angle of displacement. Sure. So what is a small angle? Well, under about 10 degrees will work for you. Now, some of you don't like that, I'll bet, right? Because some of you are like, if this is just kind of approximately right, why are we learning it? Ooh, students really want science to be exact. Right? They want to go into a science class and have their teacher say, this is exactly how the world works. But guess what? That's not what science is about. I've said this before, but you know what is not an exact science? Science. So what do we do in science? We make models. And we use those models. Why? Because they work. Is any model perfect? No, it's not, right? Right, in science, we're always open to a new idea. And in physics, we have to recognize that we can get an exact answer in very, very few situations. And up till now, in this semester, we've been really focusing on those handful of well-constrained problems where we can get an exact answer. Well, we're kind of straying outside of that now, right? This is a situation where we can't get an exact answer. But you know what? We still use this model. Why do we use it? Because it works, right? So if this freaks you out because it's not exact, well, you got to let go of that because that's not what science is about. So in summary, We're talking about oscillations. Oscillations are just wiggles, right? Wiggling stuff is just an example of periodic motion. We're going to focus on a specific type of periodic motion, simple harmonic motion. The systems we're going to focus on are a mass on a spring and a pendulum. Though these fairly simple systems can help us understand much more complex systems. For example, understanding this system can help us understand the bonds between atoms in a chemical compound. Right? We can imagine the bonds between atoms as being almost like little springs that hold them together. We can this can help us understand, walking motion, the swinging of a primate across along a branch, all kinds of different things, not just how a grandfather clock works.